my name is Paul, and today I want to present you our MICCAI 2023 paper called Point Cloud Diffusion Models for Automatic Implant Generation. Due to advances in 3D printing of biocompatible materials, patient-specific implants became increasingly popular in recent years. The design of these implants is, however, still a tedious and largely manual process that is usually carried out by trained experts. This work therefore aims to find an automatic solution to this problem. Existing approaches are mainly based on 3D unit architectures that work on downsampled patch or slice-wise data. This can lead to a loss of detail or context information, and the chosen shape representation, namely a high-resolution voxel representation, can be computationally very expensive to handle and of course also requires a lot of GPU memory. This is why we present point cloud diffusion models for automatic implant generation, a novel, non-deterministic approach that is based on a much more memory-efficient surface point cloud representation of the anatomical structure. In our work, we effectively combine a point cloud diffusion model with a voxelization network to solve the implant generation task. Let's have a quick look into our method. We define implant generation as a shape completion task. Starting with the binary segmentation mask of a defective anatomical structure SD, we aim to find the complete version SC of this structure. The implant I can then be derived from the Boolean subtraction between SC and SD. However, as performing the shape reconstruction task in this high-resolution voxel space is computationally very expensive and memory demanding, we decide to first obtain a point cloud representation of the defective structure by running marching cubes and performing a Poisson disk sampling, thus obtaining our initial point cloud Z0. This point cloud then serves as input to a point cloud diffusion model that performs the shape reconstruction task in the point cloud space. To train this point cloud diffusion model, we first define a forward diffusion process that gradually adds noise to the points belonging to the implant. In this picture, it's the gray points. We then train a neural network to gradually remove noise from points. During inference, we can then take all the condition points Z0 that we obtained before, sample some random points from an N01 distribution, and go through the whole reverse diffusion process. This then looks like this. As we condition the reverse diffusion process on Z0, the network effectively reconstructs the shape of the skull. We then pass this completed point cloud X0 through a point cloud voxelization network that gives us the voxel representation of the point cloud. This voxelization network has two main parts: some neural networks, namely a feature extractor to encode some global and local features of X0, an offset estimation network that upsamples the point cloud, and a normal estimation network that estimates the normal vectors of the upsampled point cloud. This upsampled oriented point cloud can then pass through a differentiable Poisson solver to obtain a dense voxel representation of this point cloud. Due to the differentiability of this Poisson solver, all the network parameters for feature extraction, offset estimation, and normal estimation can directly be trained on a simple mean square error loss between the ground truth and the estimated voxel representation. Let's have a quick look at some results. For evaluating our method, we choose to compare to 3 different approaches from the Auto Implant 2021 challenge. We compare the dice score, the boundary dice score, as well as the 95 percentile Hausdorff distance. By checking the reached evaluation scores, we see that our method produces very competitive results and even outperforms the Auto Implant 2021 winning approach in some of the metrics. By visually comparing the methods, we find that our method produces the smoothest surfaces that look closest to the ground truth. It also produces the implants with the fewest artifacts. By checking some results of the skull break dataset, we can see that our method reliably generates implants for defects of various size and shape. In this paper, we presented a novel method for automatic patient-specific implant generation that relies on a sparse surface point cloud representation of the skull. Our method is non-deterministic and allows for the generation of multiple reasonable implant designs. We reach competitive evaluation scores and were able to show that we can produce high-quality implants. Thank you very much for watching this video, and make sure to check out the code, data, and some further information on our project page.